Let's talk about the interpretations of a rotation matrix as linear mappings that are, in some sense, important. So there are a number of interpretations of rotation matrices. I'm going to talk about two of them, which are I find the most prominent and most useful ones. So the first one is in words. Let me tell you in words, and then try to justify it with mathematics, some algebra, some linear algebra. So in plain English, this goes like this. So let's suppose I have a point, okay, on this rigid body. Let's suppose I have a point right on this rigid body, Q, okay. And I draw a position vector from the origin of the body reference frame to Q. So let's suppose this vector, think about this vector, let's call that vector V, okay. And what I want to do is I want to express this vector V in the body coordinate system. In other words, we typically write the coordinate system as sigma B. This is a coordinate system that consists of the origin, this origin, let's call it lowercase OB, XB, YB, ZB, right? Okay, so what I'm coming back to what I was doing. Let's suppose that I want to write express V in this coordinate system sigma B. What does it mean to express a vector V in a coordinate system, you might ask? Now, the thing is, vectors like V, right, they exist without reference to any coordinate systems, right? I could have thought about this vector V that I've just drawn on this rigid body, without thinking about any coordinate system. In other words, delete these coordinate systems, all these B coordinate systems, W coordinate system, whatever clutters the page, delete them. You could still have thought about this vector V, right? So it exists as an independent entity from the coordinate systems. Now, for convenience, you introduce these coordinate systems to do some algebra, analytic geometry. But once you introduce these coordinate systems, then along with it comes components of this vector along these various vectors that define the coordinate systems, right? So when I say express a vector V in a coordinate system, I mean take its components along these vectors that define the coordinate system, right? So in other words, if I am saying I want to think about the expression or the expression of the vector V in the B coordinate system, or the body coordinate system, what I mean are these three numbers, okay? I'm going to write V, and I'm going to put a superscript B. This is just going to remind me that I am expressing the vector V in the B coordinate system. And this is equal to, one way to write this is the following, V dot XB, V dot YB, and V dot ZB. Okay, so I'm taking all the dot products of V with these vectors X sub B, Y sub B, Z sub B. And another way, so this is let's say, a column vector, right? A way of writing it as a column vector with some mild abuse of notation here. I can also express this as V dot XP is the component of the vector V along the XP direction. So this is the magnitude, this is the direction, right? Direction, magnitude. So essentially what I'm just saying over here is that I have this component along that direction, right? But I also have plus Y dot YB, this component along the YB direction, plus V dot ZB along the ZB direction. Okay, so this is another way of writing this. So this is the expression of V in the body coordinate system. Now you might ask yourself, what is the expression of V in the W coordinate system, world coordinate system? How would you do that? So think about taking this vector, this whole vector, transferring it exactly over here, and trying to find the components of V along the XW, YW, ZW directions, right? So so essentially the expression of V in the world coordinate system would be the same thing, X dot W, XW sorry, v dot xw, v dot yw, v dot zw. In other words, again with some abuse of notation, I can write this as x dot xw, v dot xw in the xw direction, plus v dot yw in the yw direction, plus v dot zw in the zw direction. What I want to do, what I want to see is that, can I write vw, the expression of v in the w coordinate system, as some linear mapping here times applied to the vector expression of v in the b coordinate system. It turns out that this question mark must be replaced by the rotation matrix between the world coordinate system and the body. Okay, it turns out that this is true. Well, you might ask yourself why. Well, let's think about this. Okay, let's think about this. So xb, vb has this decomposition. Expression of v in the x coordinate, b coordinate system has this decomposition, and expression of v in the world coordinate system has that decomposition. Now let's do some algebra. Okay, so let me let's do this. Let's start with vb as v dot xb plus v dot yb plus v dot zb. Okay. Very good. And now what we're going to do is we are going to take the dot product of this expression, okay, with xw. So what I'm going to do is I'm going to take vb dot xw. Okay, what does it give me? It gives me v dot xb dot xw plus v dot yb dot xw plus v dot zb dot xw. Of course, I use the fact that the dot product distributes over the vector addition, right? Now, what are these numbers? Those numbers. Take a good look at them. I'm going to scroll up. Look at those numbers because they are dot products between vectors, right? Dot product gives you a scalar. Each of these is a scalar or a real number. So take a good look at them. I'm going to scroll up. Look at these numbers here. Are they the same? They are absolutely the same, right? Those are the exact same expressions that we have over there. Similarly, if I take vb dot yw, I'm going to get v dot xb dot yw plus v dot yb dot yw plus v dot zb dot z. Oh, okay, I made a mistake here. This should have been xw. This should have been yw. Okay, sorry about that. Now again, the ones that are marked, these things are the first row. This, that, first row. The ones that are on the second row here, these things, right? They are the second row here, right? Exactly these numbers. And again, similarly, vb.zw is going to be equal to vxb. Well, I can just get rid of this expression and v actually. This is just a decomposition of the vector along those vectors xp, yb, zb. So this is perfectly reasonable, correct to write, perfectly mathematically correct to write. Anyway, I'm taking the dot product of v with zw, and I'm getting and finally these numbers here are exactly the third row of the rotation matrix, right? In other words, what I can do is I can collect these things in a vector, and notice that that's the expression of v in the world frame, right? v dot xw, that's exactly how we defined the expression of v in the world frame. And what I'm going to do is I'm going to write this whole right hand side as a matrix and a vector product. Right, this is the first row, this is the notice how just a sec, give me a second to write this. Notice how this matrix times this vector gives you exactly this, that, and that as the first, second, and third rows of the operation, right? Which means, and finally notice that this guy right there is actually expression of v in the body coordinate system. And notice, what the heck is this? This is exactly the rotation matrix of the body with respect to the world. So what did we see? We actually exactly proved that this was the case. So long story short, if you have a vector and you want to you have an expression of the vector in the body coordinate system, in order to find the coordinates or the expression of that vector in the world coordinate system, you multiply the original expression in the body coordinate system on the left with the rotation matrix between the body and the world coordinate systems. Okay? That's a long story short. Another interpretation of the rotation matrix is that let's now suppose this is the second interpretation of the rotation matrix, okay? Let's suppose you have a coordinate system, just the one coordinate system, okay? Since there is no source of confusion here, I'm just going to call it xyz, okay? One coordinate system, and the vector v that is expressed in this coordinate system, okay? So essentially, I'm going to go ahead and express v in this coordinate system, and it's going to be, of course, v dot x, v dot y, and v dot z, right? Let's suppose that you have this. Suppose you want to rotate this vector along the z direction, right, by some amount, by some theta, okay? There's a rotation matrix that corresponds to that, right? Essentially, okay, let me explain this in a different way. Let me explain this as having two coordinate systems. That's going to be easier on me. Sorry about that. Let's go back. Let's suppose I have a coordinate system, one coordinate system just like this, x naught, y naught, z naught, and another coordinate system. Let's suppose, for the sake of argument, just rotate it about the z naught axis by an amount theta. Okay, so only x1, x naught and x1 make an angle theta, y naught and y1 make an angle theta too, but z naught and z1 are exactly in the same direction. Okay, let's suppose we have two coordinate systems. Now, the rotation matrix that corresponds to this rotation is going to be given by, you can double check by applying the formula above, is going to be given by cosine theta. Well, this c sub theta is an abbreviation for cosine theta, and s sub theta is an abbreviation for sine theta. Okay, so anyway, so returning to the rotation matrix, this is going to be given by cosine theta minus sine theta, cosine theta, 0, 0, 0, 0, 1. Now the next interpretation again starts with a vector. Let's suppose we have a vector, this pink arrow suggests we have a vector v. Now what we want to do is essentially we want to rotate this vector v by an amount theta about the z naught axis, okay, and then find the coordinates of the rotated vector in the zeroth coordinate system. How would we do that? Well, it turns out that you just write the components of v in the zeroth coordinate system by just doing the same thing, v dot x naught, v dot y naught, v dot z naught, okay? And then if you multiply this vector v naught by this rotation matrix, you're going to get another vector, right? It's going to get rotated by, like that. It's going to get rotated. Let's call it v prime, right? V prime. And the coordinates of V prime in 0 is going to be given by this by the result of this matrix vector product. So in other words, the coordinates of V prime in the zeroth coordinate system is going to be given by what? Essentially, take this R01 times V0, which is essentially going to be cosine theta minus sine theta cosine theta 0, 0, 0, 0, 1, right? V dot x naught, V dot y naught, V dot z naught, which is going to be equal to what? V dot x naught times cosine theta minus V dot y naught times sine theta. V dot x naught times sine theta plus V dot y naught times cosine theta and V dot z naught. Okay. What I'm saying is this is the component V. This is equal to V dot times x naught, V dot times y naught, V prime dot x naught, V prime dot y naught, V prime dot z naught. Okay, this is equal to that is what I'm saying. Okay. Yeah, that's pretty much the second interpretation of the rotation matrix. And those are the two interpretations that I wanted to cover today. And before I end the discussion about rotation matrices, there is one more thing that I want to cover. Those are the properties of the rotation matrices itself. The set of rotation matrices are called special orthogonal group because if you take an arbitrary rotation matrix, let's take a matrix, let's take an arbitrary 3 by 3 matrix, okay? It has these elements, of course. It has these elements, of course. If these elements are, so let me call the first column R1, second column R2, third column R3, okay? These elements are such that, if these elements are such that, you know, if R11, R12, R13, R21, R22, R23, etc. are such that the first column and dot the second column is 0, the first column dot the third column is 0, the second column dot the third column is 0, and R1 squared, the norm of R1, the norm of R2, the norm of R3, they are all equal to 1, okay? We call this a rotation matrix, okay? So essentially in matrix terms, this can be written as R times R transpose equals R transpose times R equals the identity matrix. Remember, the identity matrix is the matrix with ones on the diagonal, which also implies that the inverse of a rotation matrix is actually its transpose, okay? This is true only for rotation matrices, you see. Well, not only for rotation matrices, but in particular for rotation. In general, this is not true, is what I'm trying to say, right? The transpose of a matrix is in general not its inverse, but for a rotation matrix, it is true. And so the set of rotation matrices is called the special orthogonal group in abstract algebra, okay, is given by matrices in 3 by 3 such that R times R transpose equals R transpose times R equals identity matrix, and the determinant of R is +1, okay? That's where the special part of the orthogonal group comes from, okay? So this is a property of rotation matrix. And finally, before I end our discussion of rotation matrices here, I want to make sure that one thing doesn't go unnoticed. This is the composition of rotations, okay? So suppose you have a world coordinate system again, ZW, XW, YW, and you have a rigid body that has rotated with respect to that and gave you, let's say, x1, y1, z1. Actually, let's call the world coordinate system as x0, y0, z0. And then you have another rigid body that's attached to this first rigid body, and that has rotated with respect to the first rigid body and gave you z2, y2, x2. Okay? In other words, you know the rotation matrix that goes from 0 to 1. You know the rotation matrix of the second rigid body with respect to the first rigid body. What you are looking for is the rotation matrix between the second rigid body and the 0th rigid body, or it could be the world, for example, right? It turns out that this, by the knowledge of R01 and R02 allows you to compute R02 in a simple manner. It turns out that R02 is simply equal to the matrix multiplication between R01 and R12. Okay? So once you do that, you essentially find all the dot products between the x2, y2, z2 axes with x0, y0, z0 axes by just looking at the components of the resulting matrix multiplication. Okay? That ends our discussion of rotation matrices. And essentially the rigid body transformations are, you just take a point on the rigid body, maybe it could be the origin of the coordinate frame that you implanted on the rigid body, for example, and the dot product between that coordinate system with the world coordinate system, and there you go, you're tracking the motion of a rigid body of a certain rigid body. Okay, we end this here.